A software developer optimized the program, but nobody congratulated him on the team because it was written in Python. A colleague even commented that it doesn't matter because for a program to run, it needs to be written in C or Rust. Everybody knows that programs written in Python don't run, they stand still. And to add even more to this insult, they shared this video. So this hurts me right here, and I bet it hurts it too, so we gotta talk about it. So I work as a software architect at Sauce Labs. I do some part-time training and consulting. I wrote a book about implementing a clean architecture in Python. I blog. In my spare time, I learn how to ride a motorcycle and how to maintain it. And I have this mission of propagating, educating people on software architecture and software engineering. So there is less chance, less second guessing, more reliable processes, and so on. And there is no better topic for this than performance. And I know there have been like 6 talks on performance in this conference, so I'm glad you don't have enough of them. I can assure you that this one is different. This one is more about a professional approach to performance and career development. So it's unlike our other talks. Right, so let's consider some Python code. So it starts from an enum with 3 elements, nothing fancy. And there is a class with a method that accepts a single argument. In the first line, we check if the argument is one of enum values. If so, we get a current timestamp in float, and we do some assignments on the objects, nothing really fancy. Okay, so the point is, one of these 4 lines is 2 to 3 times slower than all other individually. And my question to you is, which one is it? If you think this is the first line, please raise a hand. Quite a few. Not too many, not too few. The second line, the if statement. Yeah, I can count a few people too. Getting timestamp. Okay. If I didn't know what was going to happen, I would vote for that too. And the assignment. Okay. Also, not too many people. Okay. How did you know it without running this code? You eyeball it, right? You just looked at it carefully and figured out, oh, this might be it. The other thing is some intuition. Maybe you noticed some familiar part and you know that this might be slower, so that's why you chose this particular answer. Unfortunately, when you run the code and you actually measure it, the first line is the one to blame. So the first point is that intuition or eyeballing are not good companions when it comes to dealing with performance. And now, but still you can sail through life and your career, well, eyeballing stuff. And if you even grow a bird, you may look like very smart. But relying on intuition is not very reliable because if your knowledge is really imaginary, this may lead to imaginary performance improvements, so we don't want that. And the best birthday present for such a person is a stopwatch. So to actually measure things and get the output that I just showed you, we can use a tool called Line Profiler. It's a pip installable package, and you can well, import profile decorator, put it on top of functions that you want to measure, and then run it from a console, passing line profile equals 1 environment variable. You will get another command that you run, and boom, you get the same output that I just showed you, which is a nice visual way because it nails down exact line where is the problem. So the first takeaway is whenever you do anything with performance, act on data, not intuition. Terrible companion to do so. You measure before to know where the problem exactly is. We'll get to it. During the optimization to know when to stop, and at the end to know where you got. On another occasion, imagine you wrote the following piece of code. Again, very simple snippet. 3 elements list and some function that checks if an element is in this list. Okay, nothing really fancy, Maybe you are already itching to do something about it, but a colleague on your team suggests to you, hey, let's use tuple to make it run faster. Good advice? Bad advice? Hard to change? I don't know if it's a good advice because I haven't measured yet, but this change itself is trivial. You just change the square brackets with parentheses. But if you've been writing Python for longer than a couple of weeks, you probably know that for efficient lookup, you need something else, like a set, like a specific data structure. And this is faster, although we haven't measured it yet. So these are two pillars. Once we are past this basic, we can actually start talking business. So the first one is measuring, getting data to compare results. And the second one is data structures. But again, I'm making a claim without proving it with any data. So let's prove it. OK, we know that set is faster. How much it is faster? And is it worth to do it? So we'll use another type of stopwatch that's bundled with Python. It's called timed. So you can run it from a console, just calling timed module and passing the code. So in our case, we'll just pass the creation of a set and yeah, the lookup. All right? Wrong, because timed, what it does, it will rerun the code multiple times and measure these times to see how long it takes. Unfortunately, the set is created once, or if it's a list or a tuple, you do the lookup multiple times. So it's like measuring this gentleman's height with hair and shoes. Not very accurate, you just get too much. But the timed has this feature of setup. So this is another snippet of code that's run just once in order to set the stage. So eventually you should end up with something like this, when you have a creation of collection in setup and the lookup in the second argument. And if you run it, you will see that yes, set is indeed faster by 40% for 3 elements lookup, so serious business. But it's a bit surprisingly that the tuple is also faster by 10%. So the person making a suggestion wasn't technically wrong. Again, is this a problem worth addressing? So sometime back, Pydantic released a version 2. And according to different benchmarks, it was faster between 4 and 50 times even. But the thing is that if Pydantic in your code takes like a 1% of time, and you speed this 1% of time 4 times, you're solving a micro problem and getting a micro profit. So while it may look very attractive to optimize all the code, replace all the lists and so on with structs or rewrite the project in different languages supposedly faster, that just might not be the best idea. So being a professional, it's not just solving the problem. I know you're perfectly capable of doing it. It's also choosing the right problem to solve. And for this, you need to see a big picture. And reverse to that is being fixated about small things. So to answer the question of this talk, like when to bother about performance, is you need a solution to be fast enough to be considered working. So for example, when you receive messages from Kafka, the protocol assumes that the consumer needs to consume the message and actually commit the offset in a couple of minutes. If you don't do it in these minutes, the program will be considered not working and the message will just go elsewhere. So it's just not working. The other example, assume you handle a webhooks in the form of HTTP request from a provider and they require you to respond in 30 seconds with 200 OK code. So if you don't make it, again, it's not even working. So it's worth to do such things in advance before you discover it's not really working. The other one is required for user experience. So of course, the human brain only reacts in, I don't remember exact number, under 50 milliseconds. So anything faster than that will not be that much of a benefit. But if it works slower, it's just painful to use it and the user may just give up. The same goes for your own scripts. If you wrote your own scripts, your own project, and it just runs painfully slow, again, this is your user experience. So still, you might be motivated to do something about it. And the last one is a competition is faster and it matters, meaning the customers have different companies to choose from and they will pick the fastest one because it matters for them. So not only when, but also where to improve is important. And to not lose sight of a big picture, like you must stop worrying about small things and irrelevant ones. So let's imagine someone revived Nostradamus, a famous doomsayer that always sees threats everywhere, speaks about imminent demise and so on. And you have such a person on your team because they learned how to code. And they see threat everywhere. And you know that you have 3 persons like this in a meeting, it's like getting bogged down just like a Python 2 project after bumping packages. So you don't want that. You need to manage it somehow. And now one of the myths that I keep encountering is that using classes makes your code slow, or using abstraction layers make your code slow. Okay, let's check that. So another example, let's use an approach called the clean architecture, when we'll have separate classes for doing different things. So first class will be actually coordinating the whole process, first creating some order class, then using repository, which I tell in a second what it is, to save it, and then repository to actually save it to the database. So this is quite a few abstraction layers. And if you measure the overhead, how much time you spend because of these, it's 10,000 nanoseconds. Is it big? Is it small? We need a big picture. So if it's our 10,000 nanoseconds is this, and we compare it, for example, to time needed to send a message to a broker like Kafka RabbitMQ, it becomes very, very small. Also, I did this trick with units to scare you with 10,000. So yeah, that's a pure manipulation here. Yeah, so it's almost nothing, and it's only visible because I had to round up 0.6 pixels to 1, because it just wouldn't be shown at all. And if you add more typical things that happens, for example, during handling HTTP requests, like committing transaction, it's completely off. Yeah. And then, even less impact, switching from 3 elements list for lookup to set. You see? In relation, it's nothing. Means nothing. Yet this is something that people argue about, get very agitated, like for no reason, really, if you consider the big picture. So the tricky part for you to make the most out of this presentation is you need to look at your context and how fast enough is it in your context. I come mostly from web development, so in my case, request takes 100 to 200 milliseconds, and that's reasonable. Like you may have just different numbers, but again, the technique is the same. You see what's the big picture, and you see if the improvement is worth doing. And let's just check how much the single abstraction layer costs, just for the completeness. So I will just use time. On the contrary, it works pretty reliably. So if I call time through an abstraction layer of a single function, it's 84 nanoseconds. Not sure if this is good or bad. So I'll just remove the abstraction layer. Okay, and it is faster, as expected. But the difference is less than 30 nanoseconds. So it's, it's not that much. So if we are doing web development, for example, and we target like tens of milliseconds, then this doesn't really matter at all. And the things are getting better, because with experimental JIT on 3.13, it's almost half of a difference. So in summary, it's not that bad, and it's getting better and better. Apart from that, if someone is still afraid of abstraction layers and so on, you do need to realize that libraries you use, your favorite ones, also do have them. And it's like a similar realization to like someone is afraid of skeletons, but they need to know that they have one inside of them at all times. So you can't really avoid that. And these are not steps to another floor. These are abstraction layers, this pattern in the right upper corner. These are abstraction layers of SQL alchemy when you establish a connection to a database. So it's still a lot, and yeah. So when you realize, you don't actually worry about it, because you know you are not able to actually add that many levels of abstractions that would actually impact performance. But if you don't know, then, well, you're scared of what might be coming. But speaking of Nostradamus, I wanted to say that if you know a person like this, they are not a villain. It's actually very, very good to have such a person on your team, especially when others are oblivious to threats, because there's always a value in, like having a second opinion and also someone who is more careful than others. So, you know, between being right and wrong, there's also a third option. Like, they are technically right that the layer of abstraction has an impact, but it's to the point that this is meaningless when you consider a big picture. And by the way, this is completely meaningless. First of all, like, some languages like Java are smart enough to notice that this particular benchmarks of running nested loops doesn't make sense, so it just removes it while self-optimizing. And the second one is when you find a way how to make money by running empty loops, just let me know, because I would love to know this trick. So, you know, it's just not realistic, not realistic benchmark, and it's completely meaningless. Yeah, so it's good to have some context. And what is also good to have on a project are tests. And tests have two paradoxes. There are never enough of them, and they are never fast enough. However, at times, you might want to do something about the performance, and it's not always a hard thing. So let's consider a project that was developed with a moderate intensivity for 2 years. It has 500 tests, less than 10 of them uses database, but they are completely irrelevant. Everything uses mocks. So it should be blazing fast, is it? Like, people usually think that, okay, this will run in less than a few minutes, maybe even less than a minute. So this particular project, its test suite was running for 10 minutes straight. Like, what? So if something like this happens, you may suspect that there is something silly in there, and it needs to be fixed. So I will present you a distilled problem and show you what the issue was, just to satisfy your curiosity. So just to make it simple to replicate, let's just run 1,000 empty tests. Doesn't matter. I mean, there will be some modification, of course. And this test, like, is using a fixture that is creating an auto-spec of some class. Okay, so in this code snippet, there's only one line that actually does something, and it is a problem. So there is a special edge case that if the class that you create auto-spec for is big, like it has a lot of attributes, then this takes a long of time. So even though you may have been creating auto-specs for every test, you may have not even followed into it. This is just some very funny edge case. So yeah, so I showed you a distilled fragment with this, you know, visible in plain sight. What if you have thousands of lines of tests? How to find that needle in a haystack? So in this case, you need to profile your tests. And you can use cprofile, which is built in Python. Again, Python module cprofile. You can output to standard output. You can output to a file. And then run pytests on the file with the tests. This will create this outprof. And since I want to make it more visual, to be visible, I will use a tool called SnakeViz. But again, there are many of them, so you can use others. Also built-in support in your IDEs. And after installing SnakeViz, I put this file, and the website opens with my browser, and I see this. This is a flame graph. And it's completely unreadable because PyTest has lots of layers of abstractions. So they are all occupying space here. But in the right down corner, there is this fella for search. And if I enter the name of my file, again, I end up with this fixture name. So I know where to look at it. So that should be enough to track down the problem and then do something about it. The other tool that you can use to quickly profile your tests without sweating too much is PyInstrument. Then you just, again, another package you install, you ask it to report the results in HTML format, so it also opens a web browser, and you put a script. So this is not running PyTest. Like, you need to do this missing part by yourself to make it into a proper script. And the output is even much more friendlier, because at the top, you see that the entire script to 30 seconds, and the 13 and the problematic fixture over 12.5 seconds. So there's your culprit. It wasn't very hard. So the optimization itself is very simple, I would say. But again, the trouble is not the optimization. I'm pretty sure you are capable of doing that, or Google it how to do it. The problem is to finding it and knowing where to strike. So in this case, instead of creating a fixture on every test, we created just once. So this is now great. Works blazingly, it runs blazingly fast, but it doesn't work. Simply because tests tend to modify fixtures by calling methods on them, and you need to have a clean slate between the invocations. So there's luckily a way in the mocking library. There's a method called resetMock that's very fast, regardless how big the original class was, and just lets you, maintain a clean slate. So the optimization itself is simple. You find the heavy operation, the costly one. You do it rare, ideally once or not at all. And then if you need something else, but you need to make it faster, then you do it, and you're off. So, when you find your test slow, instead of going in blind and trying to optimize various things, just profile them first, because there might be some easy wins for you lurking there. Don't use your crystal ball or intuition when dealing with performance. Okay, and the last but not least, my favorite myth is that Python is not suitable for building high-performance systems. Well, because it's slow, of course. So I wish I could tell you about all the examples of high-performance systems that run on Python, but I can't. So let's just talk about tanks instead. So in the 30s, there was this idea in Great Britain of so-called cruising tanks. And as you may imagine, they were supposed to be faster, to just be faster than others. It's a little known fact that very few people know that tanks have also different attributes, like armor, like weaponry, like crew members, and so on. And of course, tanks are not programming languages, but if you optimize a tank for speed, then some things get in your way. Like, you would like to limit the weight of the tank. So what you do, you make an armor thinner. But if you also don't have an engine available that's fast enough, well, your cooling starts failing. So, it's just never that easy. And also another little known fact, you don't race tanks on a racetrack, right? So with programming languages, it's similar, because, again, speed is not just the only factor. Like, there's a community, there are available libraries, there are different ways how it's built, what's the ecosystem, and so on, and this all needs to be considered. So instead of asking, will Python be fast enough for building high-performance system, their first question should be, how fast is it enough? So, like, how fast do I need to be? And then decomposing further this high-performance system, do I care about latency, how long a single request takes? Or do I care about throughput, how much data can I process in a unit of time? Then, what are requirements of the system? Like, what does it do? Like, selling e-books is a pretty simple problem, because there's infinite stock I don't need to worry about. If I sell conference tickets, it's a little more harder, because I can't get out of them. But if I'm selling tickets to Taylor Swift performance, this is a completely different topic. And programming language have very little to do here, actually. So once I understand what the problem is, I need to pick the right data structures and databases to offload, of course, the heavy tuning to them. And I need to wonder where the bottlenecks will be. Like, will it be database? Will it be network? Will it be actually the processing? Because, if I manage to offload the effort to database, Go or Rust will not be waiting faster for a database than Python. They may be faster in processing the output, of course, but if it's small enough, it just may not matter. Then how will I scale the system? I need to figure this out. Should I use async I/O? Should I use threads to choose the more appropriate? Is it I/O bound? Is it CPU bound problem? And only then I can actually pick the programming language, once I have those things sorted out. So the first thing is we understand the problem. What are we need to actually do? Like, is it data processing? Is it web development? Is it something else? Then we design the architecture that offloads as many work to like databases and other components, so we don't have to write it by hands because it's not trivial. And then we choose the programming language at the end. So to add something to that, Charlie Marsh last year, a creator of Rust, by the way, of Astral, he said that it's not just Rust that makes Rust fast. But by the way, writing linters formatters, I think this is one of the things that Python is not the best suited for right now. But the thing is that it's not just the language that makes things fast. It's also various optimization techniques that needed to be learned and applied over time. So I don't want you to think that, yeah, Python, you can do anything with Python. The fact is that you don't actually. But it still can do a lot. And it will be better over time. So a few takeaways I want you to have out of this presentation. So the first one is, if you are to be serious about performance, you'll start from learning the data structures. You don't need to know how to implement them. No, no, no. You just need to know different types exist, what's the difference in terms of performance. And you learn how to profile. You don't need to be an expert on it. Just have 1, 2 tools at your disposal that you can use anytime without breaking too much sweat. For starters, you could try TimeIt and PyInstrument because out of all I know, they are the easiest, the simplest to start from. And remember that intuition and performance improvements do not go well together. It's just don't. Even if you do have a track record of guessing right, things are getting very tricky the larger the system you're trying to optimize is. And the bottom line is that, yeah, the Python is getting faster over time. We have plenty of attention in this area right now, which I think is a great thing. But even right now, you don't have to wait for it. You don't have to wait until Python becomes fast enough. If only you ask this question, OK, how fast do I need to be? And then you ask if Python can make it. So that's it for me. I'm Sebastian. You can catch me in the venue because we won't be taking questions right now. But yeah, I'm here available for you. So thank you for your attention.
Thank you once again to Sebastian for the wonderful talk. First time I've heard mention of Nostradamus at a Python conference call for some time. As he mentioned, there's no Q&A right now, so we've run out of time, but please catch him outside in the venue or ask online. We will have our next talk in 10 minutes. You've come for a Python conference, now do a PR review. Please give it up for Sebastian. Thank you.